theorem, property of being tricolorable is preserved under Reiter-Meister moves. And remember, each Reiter-Meister move describes sort of there's one direction that increases complexity and one that decreases, except for the type 3 move, which just kind of slides stuff around. But it's preserved under Reiter-Meister moves. So to check this, we have to check it for each type of Reiter-Meister move. Maybe it's not so clear what this means. But before we go over the proof, let me mention what's called a corollary. I learned a long time ago, if you're a little snotty, or snobby, I guess, you say corollary instead of corollary.
Who says that?
It's in the dictionary, Luke. British people. Any snobby way of saying something in English is almost everything is due to the British. Right? They were the ones that originally had English, right? It's not like Americans had English first and British people conquered German speaking the language of the Americans, right? Either every projection of a knot K is tricolorable, or no projection of K is. So it's sort of it's all or nothing. So if you look at any projection of K and it's tricolorable or not, whichever one it is, every other projection of K will be that same way. So you can, I guess it's like a Three Musketeers corollary. Right, if you know Three Musketeers. Alright, so okay. Alright, anyways, so in the Thursday's class video, somebody's voice seems to show up a lot, but I won't say who. So proof. Suppose you have two diagrams or projections. I'll call them D1 and D2. So suppose D2 is obtained from D1 by a type 1 move that increases crossing number, if it increases the number of crossings. So if you look at the picture, right, it looks like here's the dash circle thing, here's a strand in here, and I just labeled this D1, right? So D1's the name for the whole projection, and we're focused on the part that's inside this dash circle, and then we have a move, type 1 move, I guess, that took us to another diagram that differs within that dash circle. So call that D2, and so in here, you have something like that. I guess trying to show the property of being tricolorable is preserved, we assume this diagram D1's tricolorable, then we try to get a tricoloring somehow from here. So now, obviously, we can't see what's going on outside, right? If we just started saying, like, look at it crossing outside this dash circle and change or do something, then it's going to sort of start a cascading effect. You can kind of see that if you've been tricoloring knots and stuff like that, how if you have a tricolorable diagram and you just try to change the colors at one crossing and fix everything, it kind of can end up ruining the whole thing. So you can guess that what's going to happen is the tricoloring we obtain for D2 is basically should be the same outside, but inside is going to be a little bit different. Eunice?
So all knots can be tricolored except the unknot?
No.
Oh.
One of the last homework problems was that the figure 8 knot is not tricolorable. So that shows that the figure 8 knot is not the trefoil, which is tricolorable. But that doesn't show that the figure 8 knot is not the unknot. Okay, because it could be unknotted. But on this new homework, which has a problem I pushed from the last homework, we can now do 5 coloring. And it'll turn out the unknot's not 5 colorable, but the figure 8 knot is.
Why?
So that shows that the figure 8 knot is actually different, not only from the trefoil, but from the unknot. Because every time you find a new knot, you can check it. Let's say I gave you a third knot, and I want you to show it's different from the trefoil, the figure 8, and the unknot, right? If you have to check it with all 3 now, so it gets more complicated. So to make those tables in the back gets more complicated. So someone was like, did you have a question? It's like, why? Well, in general, you can do what's called end coloring. So we're not really going to get into that because it turns out there's only so far you can sort of really get. It actually works better than you might think, but sort of end coloring, it gets more involved and you have diminishing rewards, I guess. Okay, so alright, so suppose D1 is tricolored. Suppose D1 is tricolored. Let's say the strand upon which, so let's say the strand that we apply a move to is colored somehow by, say, N. Now N can be 0, 1, or 2, right? I don't think it really helps to use the colors in these. It's harder for you to take notes, but in these proofs I'll just label it with a letter that stands for one of the 3 colors. Okay, so the strand upon which the move is applied is colored N, where N is 0, 1, or 2. Hearing some chattering here. And just color the modified part of the projection with N. So the obvious thing to do is look here, and if we're not going to change anything outside, like we just want to do the most obvious thing. If we want to change anything outside, since this is going outside, this strand's like going outside of this area, right? So it's whatever we colored outside, right? It has to be the same for this part. So this part was colored in. So now if you kind of keep going around here to look at this strand and look at the next strand, which starts here, well, this goes outside, and we would imagine that it should still be in, right? So here you see parts of 2 strands, right? You see this comes in like this, and this goes out. But if you look at the original picture, it was originally colored just this one color in. And outside, like whatever it's doing, we don't really know what's going on here, but you know, the coloring for this was in, so whatever you do inside, we're kind of forced to pick in. And if you check it, does this still work? Is this still a tricoloring? Just because we were forced to make this choice doesn't automatically make it a tricoloring. Something could have gone awry. Right? But if we look here, what's the only color that appears? What's the only thing that we need to check? This one crossing, right? At this one crossing, what are the colors that appear?
N.
N, just one color, but that's okay for tricoloring, right? But what's the other condition, I guess, that we have to check for tricoloring? What's your name again? Sam? Sam?
All 3. Maybe do 3 colors.
Right, so we need to use at least 2 colors, is sort of how it's stated. And then for not, we learned last time, that means 3 colors. So outside this region, we had to see more than one color. And so if that's still going to be the case outside. So we basically color everything outside the same. In here we color N, and then it's easy to check that's still a tricoloring. So just color the modified part of the diagram or the projection